Okay, another important reminder that your exam is Thursday.
School on Friday?
Yeah.
Yeah.
The holiday is Monday, not Friday. Friday is a school day. I realize that there is a misconception about how a long weekend works, but a long weekend has 3 days, not 4. Friday is a school day. It's a short one though, so you can still take off at like 12:20 and do your long weekend thing, but no, you are required to be here on Friday. Okay? And you have something due on Friday. So you best be here to hand in that thing that's due on Friday, which is a school day. Rent over. Okay. All right. So for today, start of Unit 4. Okay? Unit 4 is simple harmonic motion and waves. Okay? Those two things get put in the same unit because one is the causative agent of the other. Okay? Something oscillating in simple harmonic motion will usually cause a disturbance known as a wave. Right? So waves is still the second half of the unit. Well, half, more like 2/3, but anyway, it's the second part. Okay? So what we're going to go over today is what is simple harmonic motion. Okay? What's necessary for it to occur? What is some of the new terminology that we're going to go over? Okay? All of that kind of stuff. And we're going to look at 2 examples of simple harmonic oscillators. Okay? That will be the extent of today's lesson. All right? So first we need to understand what simple harmonic motion is. Okay? Very simply, no pun intended, okay, it is a motion that repeats itself over and over again. All right, so a very simple example, and one of the examples of simple harmonic motion that we will go over today, okay, is that of a pendulum that simply swings back and forth over the same path. Okay, that is simple harmonic motion. It follows the same path, it reaches the same height on both sides, reaches the same speed in the middle, okay, it just oscillates back and forth. Right. Now, obviously in the real world, a pendulum will not swing forever like this. Eventually it will stop because of non-conservative forces, specifically friction. Okay? But if this was occurring in an isolated system, then of course it would swing forever. Okay? And that's why we call it simple harmonic motion. Okay, so how can simple harmonic motion happen and be maintained? Okay? In order for the pendulum to swing back and forth, what force is working on it? What makes that pendulum swing back and forth once it's in motion? Gravity. Yeah. Gravity accelerates it down towards the bottom of the arc, okay, and then gravity slows it down on its way back up the other side. Okay, then it stops for an instant and gravity accelerates it back down, okay, towards the bottom and slows it. It's always gravity. Okay? And all gravity is doing is conserving the mechanical energy of the system, right? It's turning it from potential to kinetic and back again, over and over and over. Okay, that's simple harmonic motion. For simple harmonic motion to occur, there does have to be a force that is trying to return the object to what we would call its equilibrium position. Okay, for a pendulum, okay, so if I draw a pendulum like this, it swings along an arc like this. The bottom would be the equilibrium position. That is where it would return to, okay, if there was no more energy. Okay, it's eventually where it stops in the real world. Right? There's always, however, a force that's trying to bring it back to that situation. The key here is that that force always and never succeeds. Now that might seem weird. Okay? Does gravity always get the pendulum to come back to equilibrium? Every single swing. Does it ever stay there? No. Okay? Gravity brings it back to equilibrium, and then it gets here and it's like, whoa, and it just keeps going, okay, right on up the other side. Then gravity's got to slow it down and bring it back, and it'll come back. But it won't stop there. It'll just keep going right on through. Okay? So that force we call the restoring force. Okay? It's always trying to restore a state of equilibrium. Okay? When a pendulum is hanging straight up and down, all the forces on it are balanced. Gravity is acting straight down, and the string is acting straight up. Okay, forces are balanced, that's its equilibrium position. As soon as it goes past that, now gravity is going to be dominant because now the tension in the string is acting at an angle and they're not equal anymore. Okay, everybody okay with that idea? All right, so we're going to look at two common examples. Obviously, the pendulum is one of them, okay, and a mass on a spring is another. So imagine you had just like a bowling ball, but there was a spring inserted into it. Okay, if I push on the spring and then let go, the ball will oscillate back and forth on the end of that spring, okay, just like the pendulum oscillates back and forth along its arc. Okay. So, if you've ever been on a set of playground swings, you have been a simple harmonic oscillator. Okay, you've been a pendulum. Right? Now you know from being a kid that you can't just sit on the swing and hope that it's going to get going. Okay, you usually have to pump your legs, okay, and put some energy into it because there's obviously friction in that situation. Okay, but if you had a perfectly frictionless swing and mom or dad when you were little gave you an underduck, okay, well you would just swing back and forth forever. Or until they stopped you. Probably that's what would happen as opposed to you swinging back and forth forever. Okay? And the reason for that is gravity wants to bring you back to that equilibrium position. Okay? So, other examples, vibrating guitar string, okay, or any string instrument. When you pluck one of the strings, it's going to oscillate back and forth along the same path. Okay? And obviously when it does that, it creates a disturbance in the air that we hear as sound. Right? But there has to be a disturbance. Now, what brings the guitar string back to its equilibrium position? Do you have to like pull hard on the string to make it move? Okay, does the string have tension in it? It's kind of elastic, right? Okay, elastic restoring force is very, very common. Like for a mass on a spring, the spring has elastic force in it. Okay? Same with a guitar string. When I pull on a guitar string, it wants to go back to equilibrium. Okay? And so it does. It just oscillates back and forth. Okay? All right. Questions there? All right. Now, in every case of simple harmonic motion, there is what we call an equilibrium position where all the forces acting on the object are balanced. That's why it's called the equilibrium position. In that position, for that instant, there's a net force of 0, okay, and all the forces balance out. Okay, so if I'm looking at a mass on a spring, okay, and I'm following it through its oscillation, okay, this is the equilibrium position. Right? So if I was to disturb the mass this direction like you see in number 2 here, okay, so I push the mass this way, would I be doing work? Am I exerting a force over a distance? Okay, like to compress the spring requires you to do work because you're going to put elastic potential energy into that spring. So you push it this way, okay, and then when you let it go, there's a lot of energy, elastic potential energy, in that spring, and that is going to cause it to exert a force and do work on the mass to push it back to equilibrium. Right? So as it's returning to equilibrium, it's accelerating. Okay? That force is actually decreasing. As the spring approaches equilibrium, it's less and less compressed, and it can push less and less and less. When it's at equilibrium, that's where the spring would sit if nobody bothered it. So, it's not compressed, it's not stretched, so it exerts no force on the mass there. Okay? And that's why it would rest there. Now, when it goes past that, and you start to stretch the spring, okay, it wants to pull back the other way. A spring works equally in both directions. Okay? It can push and pull, and it does so equally based on how much or how far from equilibrium it's pulled or pushed. Okay, so at this point here, okay, if that spring, if I was measuring the pushing force in that spring, okay, let's just say it would be 2 newtons. While here, also 2 newtons. It would just be pulling. Okay, now is force a vector quantity? Okay, what direction does a restoring force always go? because it looks to me that in one situation it's pushing to the right, and in the other direction it's pulling to the left, but it's always towards the equilibrium position. Okay, a restoring force is always towards the equilibrium position. That could be right or left, depending on the situation. Okay? All right. If I'm watching this thing oscillate back and forth, okay, how fast would it be moving here and here? And spoiler alert, you can actually give me a value here. Okay, picture in your mind what that would look like. Okay, the object is passed through equilibrium and now it's stretching the spring or compressing the spring, depending on which direction you're going. Eventually, what is that mass going to do for an instant? It's going to stop. Yeah. Okay, because it's going to compress that spring. It's going to run out of energy. Okay, well, it's going to run out of kinetic energy, but it's going to have a lot of potential. Okay, so at these two positions, okay, the velocity would be 0. But the force and the acceleration would be at their maximum because that's where the spring is compressed or stretched the most and where it's going to push the hardest. Okay? The maximum speed of the object actually occurs at equilibrium because the object has been pushed or pulled all the way there. Okay? That force has been acting on it all the way towards equilibrium. So the object is moving fastest at equilibrium. Okay? Whether it's a pendulum or a mass on a spring, that is true. Okay. Everybody with me there? Okay. So there's energy that is converted here. There are forces that are being exerted. Right? So there is stuff from other units in this unit as well. Okay? Those concepts of force and work and energy are still going to be part of this. Okay, if we're naming some of these positions, okay, so if I'm looking at the box on the spring here, okay, these two positions that I have circled, okay, are what we call the amplitude. Okay, that is the maximum displacement from equilibrium that the object experiences. Okay, often we hear amplitude used when we're talking about sound. Okay, you use an amplifier to make sound or music louder. All right, all that amplifier does is make the cone of the speaker move further. Okay, the further it moves, the bigger the waves it's going to produce. Okay, and you will hear a louder sound. Okay, so the farther an object goes from equilibrium, the greater its amplitude would be. Okay, and then the circles that are in purple, okay, so that would be this one and this one. Okay, that's going to be our equilibrium position. Okay, and as I said, those terms apply to any simple harmonic oscillation. Pendulum, mass on a spring, a guitar string, okay, all of them. Okay, what would I call the amount of time it takes this mass to do this and come back to equilibrium again? So to go through one full cycle, what would I call that amount of time?
Frequency.
Other one, the inverse of that. Starts with P.
Period.
Period, right. How many times it does that in a second would be the frequency. That would be the inverse of that. Okay, so the amount of time it takes for this simple harmonic oscillator to make one oscillation or one cycle is the period. That term is also familiar to us from the last unit. Okay, so we're going to use period, we're going to use frequency. Okay, those terms mean the same thing here that they meant in the last unit. They are the time for one cycle or the number of cycles per second. Okay. All right, questions there so far, guys? Okay, so in order for simple harmonic motion to occur, this must be true. All right, so if you don't have the notes package, this needs to be copied down. Okay, the restoring force must vary linearly with displacement. Okay, so it has to get bigger in a linear way with the displacement. So if I doubled the displacement, the restoring force would be doubled. Okay, that must be true for simple harmonic motion to occur. Okay, so that's fairly obvious when we're talking about a mass on a spring. Okay, the more I push on the spring or pull on the spring, the harder I'm going to have to push or pull. Okay, the further I want to move it, the more I'm going to have to pull. That one makes sense intuitively. It's the pendulum that people have a harder time with. Okay, the force that's supposed to be bringing the pendulum back to equilibrium is the force of gravity. Does the force of gravity change? Does the weight of the piece of tape on the end of my string here, okay, does the weight of that thing change when I move it out to here? No. This thing weighs the same amount anywhere in the arc. Okay, the weight of a pendulum doesn't change, and that's why people are like, wait, Mr. Coderre, if you said that the restoring force is gravity, and the restoring force has to get bigger the further from equilibrium it gets, that doesn't hold true for a pendulum because the weight of the pendulum doesn't change. And that is 100% right. And that's because it's not the force of gravity, it's how much of it is acting along the arc that changes. That does change. Okay, so let me show you what I mean. At equilibrium, so right here, gravity pulls this way. Okay? Is it acting along the arc at all in that position? It's not. It's 100% perpendicular to the arc. Okay? If I extend the arc all the way up to here so that like the pendulum would be horizontal, okay? Now, all of that same amount of gravitational force is acting right along the arc. Did you follow me there? Okay? So here, the amount of gravity that's going along the arc or parallel to the arc is 0 because it's perpendicular. Here, it's all of it. But as I move along the arc, the amount that gravity pulls doesn't change. The length of all these arrows is supposed to be the same. But okay, as I change the angle, the amount of it acting along the arc does change. Okay, there's that component of it that acts this way along the arc. Okay, because there's also a pulling force from the string or the rod, whatever the pendulum is made out of. Okay? So as I get further from equilibrium, that component gets bigger and bigger and bigger until it's 100% of gravity. As I get closer and closer and closer, that amount gets smaller and smaller and smaller. Okay? So the amount that gravity pulls along the arc, its component, its vector along the arc, gets smaller and smaller as I approach equilibrium. Because if you're thinking, that can't be right, Mr. Coderre, you're 100% right. The weight of the pendulum does not change, but how much of it is pulling along the arc does. So it still varies linearly with displacement. Okay, it's just along an arc instead. Okay. So, motion of objects with simple harmonic motion, okay, can be described by two quantities, okay, and waves will be the same, period and amplitude. Okay? Now, we could say period, frequency, and amplitude, but period and frequency are kind of two sides of the same coin. Okay? So, period is how long it takes the oscillator to make one complete cycle. The amplitude is, as we've already seen, how far from equilibrium does that object get. Okay? So, this is a diagram of one complete cycle of this mass on a spring. All right, so we're saying that in this oscillation, we're going to start at equilibrium. Okay, object is going to move out to here, its maximum amplitude, and then the restoring force is actually going to start to move it back. The whole time the restoring force is moving it, or is pulling it towards equilibrium, but it doesn't start to move until it gets to here. Okay, then it's going to pass back through equilibrium and go to its maximum amplitude on the other side, and then the spring will push it back to equilibrium. What shape does that make? A wave. This is why simple harmonic motion can lead to waves. It's going to create a disturbance in whatever medium it's traveling through that is going to cycle up and down and make a wave. Okay, everybody all right with that idea? Okay, so terminology we've talked about. Okay, the maximum amplitude occurs on either side of equilibrium. Okay, it's the maximum distance on either side that the object will get from equilibrium. Right? Now, at this point here, at the maximum amplitude, here and here, okay, acceleration is at its maximum. So is the restoring force. Okay, and so we could write that here as well. So force restoring would also be at its maximum. Its acceleration would be at its maximum. But its velocity at both of those points is 0. Okay, because the restoring force is accelerating. It's, in both of those cases, it's been slowing it down as it tries to pull it back to equilibrium. It stops for an instant before going back towards equilibrium again. Okay? Now, that also means that as the object passes through equilibrium, there would be no restoring force and no acceleration, because at that point, in this case, the spring isn't stretched or compressed. It's how it would sit if you left it alone. Okay? So it'll sit there and it won't exert any force. With no force, there's no acceleration. But it has been accelerating it from here to here this whole time. So its speed goes from 0 to its maximum. Anytime the object travels through equilibrium, it is moving at its maximum speed. Okay? What form would all of its energy be in as it passes through equilibrium? Kinetic. Yeah. Okay? All of its energy will be kinetic because the spring isn't stretched or compressed anymore. It doesn't have any potential energy in it. It's converted it all into kinetic. Okay? All right, so make sure you know those terms, especially amplitude. That's a new term. Okay, we haven't gone over that before. Okay, amplitude is the motion is the maximum distance, okay, or displacement from the equilibrium position. Okay. Questions there? Okay. Anybody need that anymore? All right, I'm just going to go back to this one here. So if I'm looking at the period of this motion, okay, for a mass on a spring, okay, what two things do you think could affect how long it takes that mass to make one cycle? Like, what are some things in this situation that if I changed them, could change how long that cycle takes? Right, the spring itself actually, okay? Because every spring kind of has what we call a spring constant. It's a measure of how stiff the spring is, okay? Every spring is a little bit different, right? Like if you have one of those clicker pens, right? There's a little spring in there. That does not have a very big spring constant because it's not very strong, right? The springs in your car are considerably stiffer. Okay, because they obviously have a very different job. You would not replace one with the other. Okay, it'd be very hard to click your pen if it had a car spring on it. Okay, so yeah, if I replaced the spring, I would change the stiffness of the spring. A stiffer spring wouldn't be able to be pushed as far, so it wouldn't take as long to make one complete oscillation. Agreed? Okay, let's say I leave the spring. What else could I change that might change how long it takes? Think. Yeah, exactly. If I put more mass on there, okay, it's going to make that spring travel further and thus take longer to go through its cycle, okay, because it would have more inertia. Everybody all right with that idea? Okay, so the two things that can affect the period of a mass on a spring are, oddly enough, the mass and the spring. Okay, so that's where our first formula in this unit comes from. Okay, the period of a mass on a spring is affected by the mass, M, and the spring constant. We use K to represent spring constant. Okay, and just for your notes, you might want to add this. Okay, mass, as is always the case in physics, is in kilograms. Okay, spring constant is newtons per meter. Right? It would be how many newtons would be required to change the length of the spring by 1 meter to stretch or compress it. Yes, Gareth, go. Right? Everybody with me there? Okay, so newtons per meter are the units for spring constant. Okay, so the formula goes like this. The period of the oscillator equals 2 pi times the square root of mass divided by spring constant. Okay, so it's not a terribly difficult formula to use, but if you're going to manipulate for anything under the root, what do you need to do to the entire formula first? Square it. Yeah. Okay, if you're going to solve for M or you're going to solve for K, you have to square everything in the formula to get rid of that root. Okay, then you can start manipulating things. All right. Questions on that one? All right, so as a simple example here, okay, if I had a ball that had a mass of 0.2 kilograms and I attached it to a spring that had a tension, sometimes we use the word tension or spring constant, of 28 newtons per meter, okay, how long would it take for the ball to complete one complete cycle and return to equilibrium? All right, so T equals 2 pi times the root of M over K. I have M and K in this situation, so I don't need to manipulate. I'm trying to solve for big T. Okay, so that's simply going to be 2 pi times the square root, okay, of 0.2 divided by 28. I forgot to start my calculator. All right, so for punching that in here, okay, we would start out with 2 times pi. Okay, and then put in a root, and we'd have 0.2 divided by 28. Okay, so that's going to take just over half a second for that mass to make one complete oscillation. Okay, from equilibrium, okay, to its maximum amplitude, through equilibrium to its maximum amplitude on the other side, and back. Okay, in every complete oscillation, the object travels through equilibrium twice. Okay, complete oscillation requires 2 passes through equilibrium. All right, so the units for that obviously would be seconds, 0.53 seconds. Okay, just so you understand where we arrived at that. Okay, a newton is a kilogram meter per second squared, but it's also a newton. Our units for spring constant are newtons per meter. Okay, so obviously the meters go away. Okay, and I've got a kilograms on the top and then a kilograms on the bottom, right? And then I've got that under the root. So the root takes care of the squared, and I'm going to be left with units of seconds. Okay. All right. Everybody okay with how that one worked? Right. Now, what about for a pendulum? Okay. What things could affect how long it takes for a pendulum to make a complete oscillation? length of the string, absolutely. Okay, now my afternoon class won't see this, but okay, if I just do this, does it oscillate a lot quicker now? Right? Like I cut the length of the string in half and that thing is oscillating back and forth a lot faster than when it was doing this. Okay, so yeah, length of the string is definitely one thing that would affect how long it takes a pendulum to swing. Okay, what else?
The strength of gravity.
Yeah, the strength of gravity. Right? This is the first time ever where no one has said the mass of the bob. By the way, the mass on the end of a pendulum is called the bob. Don't ask me why. Okay? It's just called a bob. Right? The mass of the bob doesn't affect it because all things fall at the same rate. So the mass actually doesn't make any difference. Okay? I could have a bowling ball in the end of here, but I wouldn't be able to hold it up. Okay? But yeah, the acceleration due to gravity does make a big difference. If I was to do exactly what I'm doing right now on the moon, it would look like this is happening in slow motion. Right? Because the acceleration due to gravity on the moon is 1.6 meters per second squared, whereas here it's 9.81. Okay? It would definitely take a lot longer for an identical pendulum to make one swing on the moon. In fact, it was one of the things that the astronauts did when they landed on the moon. Okay? That's a simple tool to bring along. Okay? Is just a pendulum and have it swing back and forth to get some measurements of the gravitational field strength at the points where they landed. All right, so for a pendulum, the things that affect the period of a pendulum are the length of the pendulum, L, in meters, and the acceleration due to gravity in meters per second squared. Right, so your formula is very similar. It's still 2 pi, okay, times now the root of L over G. Same rules apply to this formula. If I wanted to manipulate for anything under the root, then I would have to square the entire formula in order to get rid of the root. Okay? Everybody all right with that idea? So, why were pendulums such a common way to make sure a clock kept accurate time? Because forever, that's how clocks worked. Okay, they had a big pendulum in them. Okay, you pushed them out to one side, and the pendulum would swing back and forth. Okay, all day long, keeping, well, reasonably accurate time. Okay, why was that such a good idea? Could you reliably know what the period of that swing would be as long as you knew how long the pendulum was? Okay, that's why those kind of clocks were full of gears. Okay, based on the length of the pendulum, since you knew you were on Earth and gravity was a certain number, okay, that would swing back and forth with the same period for as long as it was swinging. Okay, and as long as you had the gears in the back made right, it would obviously keep accurate time on the clock. Okay, now, is the pendulum, if the only thing making it go back and forth is gravity, going to swing all day? And it's going to get less and less all day long, right? Okay, so most grandfather clocks also had a spring in them. Okay, if anyone has actually seen an old grandfather clock, they usually had a hole in them somewhere where you put a key in and you would wind the key, okay, and that would wind up a spring inside that would assist the pendulum throughout the day to keep it swinging. All right, and that way it would keep accurate time. Otherwise, it would run slower and slower and slower all day, and then not obviously keep accurate time. Right? Could adjustments be made to the clock? Like, what if I moved, because we did this back in the last unit, what if I lived near the equator, okay, at sea level, and I moved much closer to the pole? Is my clock going to keep accurate time? It's not, because now gravity is different, right? If I move toward the pole, gravity is going to be a lot greater, and my pendulum is going to have a different period than it did in my previous home. Right? So what you have to do is adjust either the spring, okay, or you could adjust the length of the pendulum a little bit, okay, in order to make sure it kept accurate time. Okay, so let's say we'll do this simple one here, okay? What's the period of a pendulum located on a high mountain where the acceleration due to gravity is 9.71 meters per second squared and the pendulum is 1.55 meters long? Right, so simple calculation there, we just punch in our numbers. We don't have to manipulate, okay? We're gonna have L over G, so that'll be 2 pi times the root of 1.55 divided by 9.71. Okay. Same type of input on your calculator. 2 times pi times the square root of 1.55 divided by 9.81. Okay, so that pendulum would have a length, or sorry, would have a period of 2.5 seconds. Oh, wait, I put in 9.81 when I should have put in what? 9.71, not 81, 71. Okay, now that I've made that correction, longer or shorter? I have less gravity, so it's going to be longer. Okay, not a lot longer, right? I mean, if we're talking about, moving like the example I gave you, moving from the equator to a more northerly place, it changed the acceleration due to gravity significantly, but it only changed the period by, a couple tenths of a second. Sorry, 1/10, not even 1/10 of a second, a couple hundredths of a second. Okay, didn't make a very big difference there, right? From 2.49 to 2.51. Now, your clock's running for a couple of weeks. You might notice you've lost a minute. It's not a huge deal, but if you're relying on it to be super accurate, it's not good enough. Okay, so 2.51 seconds. Remember, the mass on the end of a pendulum is called the bob. So that is plumb bob, square pence, pendulum bob, square pence. Okay. Don't watch that show. Apparently, there's research that says you get dumber by watching it.
I used to watch a lot of that when I was a kid. I was about to watch a good show. No, big series. My dad would watch. Didn't work with us.
Okay, I want you guys to try this one. Okay, I'll give you a couple minutes to try and see what the length of this pendulum would need to be to have a period of 1 second under normal Earth gravity, 9.81. Right, so I'll give you a couple minutes. Mr. Pumphrey, if you can pause it. Okay, so for this one here, obviously we know big T, okay, that's what that is, and we know little g. So we do have to manipulate this equation to solve for the length of the pendulum. So we got 2 pi times the square root of L over g. Okay, if I want to get anything out from under the root, and I do, I have to square everything. So that's going to look like this. T squared equals 4 pi squared times L over g. Okay, now the root is gone because I've squared everything. Okay, if I want to get L by itself, I'm going to multiply both sides by g. I'm going to divide both sides by 4 pi squared, and I'm left with L. All right, so now I can just plug in my numbers here. Okay, so L will be 1 squared times 9.81 divided by 4 pi squared. Right, so that'll be 9.81, because 1 times 9.81 is 9.81, divided by 4 pi squared. All right, so that is going to that is going to require a pendulum with a length of 0.25 meters. All right, so that pendulum is 25 centimeters long. Actually, I should have that to 3 significant digits, shouldn't I? So that should be 0.248 meters. Okay, Questions on how that one worked? Okay,
On the equation, is that an E or an L?
that's an L.
Okay.
Yeah, L for length.
See that?
All right, now, you've probably all seen the videos where somebody like takes a big heavy ball and like a chain or a rope and they hold it right up against their face and then they let it go and then they stand there. Okay, if you just let that ball go, do you have anything to worry about? Okay, it's a simple matter of conservation of mechanical energy. If you, as long as you don't push that ball, it can never hit you in the face because that's not how far it was. And it's obviously happening in the real world where it's going to lose a little bit of energy on the swing anyway. Okay, the only time someone's going to get that in the face is if they give it a push. Okay, and they give a little extra energy to that pendulum. But if you just let it go, okay, it will never come back higher than it left. Okay. All right. Okay, give this one a try. Okay, you're on a different planet and you took a pendulum along because you thought ahead. And you know that that pendulum is 0.65 meters long and you measure that it takes 2.8 seconds for it to make one complete oscillation. I want you to calculate for me what the acceleration due to gravity is there. Okay, Mr. Pumphrey, I'll get you to pause it here for a few minutes. Okay, let's have a look at this one. So, we're being asked to find little g, okay, and we're told the length of the pendulum, 0.65 meters, and we're told the period is 2.8 seconds. Okay, so t equals 2 pi times the root of L over g, and we're trying to solve for g, which is under the root. So the first thing we have to do is square the entire formula. Okay, so t squared equals 4 pi squared times L over g, and now I just want to swap g and t squared. Right, so g will be 4 pi squared times L over t squared. So 4 pi squared times 0.65 meters divided by 2.8 squared. What do you suppose the most common thing people forget to do is? Actually square t. They'll remember the 4 pi squared part all the time, but they'll forget to square t all the time. All right, so we got 4 pi squared times 0.65. Okay, divide that by 2.8 squared. All right, so g on that planet is 3.3 meters per second squared, or newtons per kilogram. Okay, it's gravitational field strength on that planet. What planet in our solar system would have gravity 1/3 of Earth? This would be Mars. Mars would have gravity 1/3 that of Earth. Okay? This is one of the things they didn't do a good job of showing in The Martian. Mark Watney should not have gotten tired lifting all that stuff because it should have weighed 1/3 of what it weighs here. Okay.
Can you move the calculator for a second?
Mm-hmm. All right, any other questions on that? Okay, quick review. Something we're going to use in this unit a fair amount. We learned it in the last unit, but almost never used it. Okay, and that is this relationship, that T equals 1 over F, and obviously that then F is 1 over T. Okay, these two questions are simply reminding you of that relationship. Okay, so it says here that earthquake waves travel along the Earth's surface and have periods of up to 5 minutes. What is their frequency? Okay, well, if I wanted to find their frequency, I would just go 1 over 300 seconds, because that's 5 minutes. Okay, 300 seconds. All right, and so I would get 0.033 or whatever it is. Okay, so 1 divided by 300. Okay, so 0.003 repeating, okay, would be their frequency. So way less than 1 oscillation per second, okay, for an earthquake wave. Okay, and then the opposite here for the hummingbird. A hummingbird can hover when it flaps its wings with a frequency of 78 hertz. So imagine your wings are flapping up and down 78 times per second. That's why they hum. Okay, it's literally their wings going up and down so fast. Okay, so for that one here, 1/78. Okay, and we would get a period of 0.013 seconds. So their wings go up and down in one complete cycle, okay, once every 0.013 seconds. Fast. That's why they need so much sugar water. They have a hummingbird feeder, right? That's all that's in there is just sugar water. And they burn a lot of calories flapping their wings so fast. Okay. No, we haven't done that stuff yet. All right, give that one a try. Okay, so get Mr. Pumphrey to pause it again for a minute. Okay, could there conceivably be more than one way to do this question? Like in the last unit, did we have a formula that also calculated little g, provided we knew the mass of the thing generating the gravitational field and how far we were from its center? Okay, and that's what that question wants you to think about when it gives you the altitude of Mount Everest. Okay, you could conceivably do one of these calculations here, where you could go little g equals big G times the mass of the Earth over r squared. You'd obviously have to add this number onto the radius of the Earth. Theoretically, that should give you the same number, but that's a lot more work than doing this. Okay, I've just got that formula. All I have to do is manipulate it, okay, so that I can get the gravitational field strength. So t squared is 4 pi squared times L over G. Swap the G and T squared. Okay, so you got 4 pi squared times 1 meter, okay, divided by 2.01 squared. Okay, so the acceleration due to gravity there is 9.77 meters per second squared. If we did it this way, okay, the other way, then we should have, theoretically the same number. It doesn't come out to exactly the same number. Okay? Theoretically it should, but we have to remember that our numbers, like the 5.98 times 10 to the 24, are severely rounded off. Okay, as is the radius of the Earth, the 6.37 times 10 to the 6, that's also severely rounded off. Okay, so I mean theoretically, if I had all of the digits, that should come out to exactly the same number. Okay. All right, questions on how that one works? Okay. Are simple harmonic motion problems like pendulum and mass on a spring? So remember, mass on a spring looks like this. T equals 2 pi root m over k. Are these really just algebra problems? Right, all you're ever going to be asked to do is manipulate that equation for one of its parts. Okay, so they're not overly challenging. You just have to get the hang of reading through them and knowing what's being given and what you're looking for. All right, let's have you guys try these 3 here. Okay, see how we do on those, right? And I'll get Mr. Pumphrey to pause it and give people time to work it through, and then we can look at them together. If you finish these 3, okay, there is that handout. Okay, you can start working on the problems from the handout. Okay, so we'll just kind of not worry about 3, not because it's difficult, it's just, in fact, it's because it's too easy. You're just solving for period on number 3, you don't even have to manipulate the formula, okay? So obviously on 1 and 2, you're manipulating for the 2 variables that are under the root, so again, you just have to square root, or sorry, you have to square everything in order to get rid of the root, okay? And solve for, obviously, G in question number 1, and for L in question number 2. Okay, do we need to go over either of those? All right. Okay, so I handed out a worksheet to you. Okay, this question is question number 1 on that worksheet. It goes, there's a bunch of mass on a spring questions, and then there's some pendulum questions. That's what I want you working on here, remainder of class. I do a few mass on the spring questions because we only did 1. We've done a whole bunch of pendulum questions. Okay, but like for example, okay, this one's pretty straightforward, but it is a mass on the spring. Okay, do a few mass on the spring questions, work on that sheet, remainder of class. Okay, and then if you have questions, okay, any ones we need to go over, we'll go over them on the board. Okay, if they give you trouble.